All right, let's dive right in. We're about to peel back a layer of reality to look at something that's, well, completely invisible, but it's one of the most fundamental forces that shapes our entire universe. We're talking about the electric field. And it all starts with this really simple question, one you might ask as a kid. How can one thing push another without actually touching it? We all know that if you bring two positive charges near each other, they'll push apart. But how? How does one charge even know the other one is there, especially when there's just empty space between them? This whole puzzle has a pretty cool name, action at a distance. And for the early physicists, it was seriously spooky. I mean, it seemed to fly in the face of common sense. The idea that to move something, you have to actually touch it. This wasn't just some small detail. It was a huge, deep problem right at the heart of understanding how forces work. Let's really wrap our heads around that for a second. Imagine a charge just sitting there in space. You bring a second charge close and poof, it feels a force. Okay, now take that second charge away. What is left behind in that spot? Is it just nothing? Because if it's truly nothing, then how on earth does that force magically reappear the instant you put the charge back? Something has to be there, in the space itself. And this is where the genius of scientists like Michael Faraday comes in. The solution to this whole spooky problem is the electric field. The idea is that a charge isn't acting directly on another charge way over there. No, instead, it's actually changing the very fabric of the space all around it. So here's the key takeaway. The electric field is a property of space. A charge creates this field and it spreads out everywhere. Think of it like an invisible map of potential force. So when you place a second charge into this field, it's the field right at that spot that tells the charge which way to go and how hard to get pushed. The charges never talk to each other directly, they only talk to the field. Now, to keep all this straight, physicists came up with two helpful terms. First, you've got the source charge. This is the big one, the one that's actually creating the field we're interested in. Then you have the test charge. This is just a tiny little positive charge that we can imagine placing anywhere we want, just to see what the field is doing at that point. It's basically our little probe for exploring this invisible force field. And this is where the idea becomes so elegant. The relationship is just beautiful and simple. The force that our little test charge, Q, feels is simply its own charge value multiplied by the strength of the electric field E right where it's sitting. The field does all the heavy lifting. It knows about the source charge, the distance, all that stuff. The actual interaction is just simple multiplication. Okay, so this field is an invisible property of space. I get it, that's kind of abstract. How are we supposed to picture something like that? Well, luckily, physicists came up with a really clever and intuitive way to draw it using something called field lines. And the rule for drawing these is just so simple. By convention, the field lines always show which way a positive test charge would be pushed. So if you look at the positive source charge on the left, the lines are all pointing outwards, away from it, because that's the way it would push another positive charge. And for the negative source charge on the right, they all point inwards because it would pull a positive test charge towards it. Simple as that. So let's just do a quick recap of these key rules. The field lines always point away from positive charges and they point towards negative charges. And because the force gets weaker with distance, the field's strength, or its magnitude, is the same at any point that's the same distance away from the charge, which gives it this really nice spherical shape. It's all built on that one simple idea. What would a positive test charge do? So dealing with one charge is pretty straightforward. But what happens when you've got a bunch of different charges all hanging out in the same area, each one creating its own electric field? Does it all just turn into a complete chaotic mess? Amazingly, nope. Nature is just incredibly elegant about this. The rule is called the superposition principle, and it basically says that to find the total field at any single point, you just figure out the field from each charge all by itself, and then you just add them all up. You add them as vectors, which just means you're adding up arrows that have both a strength and a direction. The fields don't mess with each other. They just add. And you can see exactly what that looks like right here. At that spot, point P, you've got fields coming from 4 different charges. The field E1 points away from Q1, E2 points away from Q2, and so on. The total electric field, the net field at P, is just what you get when you add all those blue arrows together, tip to tail. It really is that simple. And here is the math that describes the picture we were just looking at. I know it might look a little intimidating, but all this equation is really saying is that the total electric field, E,
is just the sum, that's what that big Greek letter sigma means, of all the individual fields from each and every charge. It's just the fancy recipe for add up all the arrows. So, up to this point, the electric field seems like a really clever, really useful way to calculate forces. But this begs a much bigger question. Is the electric field a real physical thing that actually exists in empty space, or is it just a convenient mathematical trick we invented to make the sums easier? And to be perfectly fair, if all your charges are just sitting still, that's what we call electrostatics, you could kind of argue that the field is just a convenience. You could, theoretically, just calculate all the action at a distance forces directly. It'd be messy, but you could do it. In that case, the field almost seems optional.
But the game changes completely the second things start to move. What happens if you take a charge and you suddenly wiggle it? What does a charge far away feel? And maybe more importantly, when does it feel it?
This is where the field shows us what it's really made of. There's a cosmic speed limit in our universe, right? Nothing, not even information, can travel faster than the speed of light. So if you wiggle charge 1 over here, the effect on charge 2 over there is not instant. A change, like a ripple, has to actually travel through the electric field, and it travels at the speed of light. So charge 2 only feels that force after a certain time delay. The old action at a distance idea completely falls apart here. It has no way to explain a time delay. But the electric field concept, it handles it perfectly. The field is the physical thing that carries the information, that carries the force from one place to another. It's not just a calculator, it's the messenger itself.
And this brings us to the final, really profound conclusion that physicists have come to. Fields are real. They're actual physical things. They're not just maps of forces. They're a dynamic part of our universe. They can move, they can change, and they can even carry energy across the vast emptiness of space. That's what light is, an electromagnetic wave. So the next time you see a spark of static electricity or feel a little shock, just remember, you're not just witnessing a force. You're interacting with a real physical field that fills all of space. And that leaves us with a pretty wild thought. If this invisible, energy-carrying reality is literally everywhere, what else is it doing all around us, completely unseen?